Hi, today we are going to discuss about um, quality of software design. So let's say and like how are we going to measure the quality of a design? So generally we can use a term like good design, good design. So how to measure this thing? So that is what we are going to discuss today. So good design means a design which satisfy which reach high quality. So good design implies quality of design is higher. Good design implies quality of design is higher. So how to measure this thing, how to measure whether the design is good or not? We measure that using like measuring the quality of the design. So to measure the quality of the design, we have four quality factors. The first one we can say understandability. The second factor, adaptability. Third factor, coupling. And the fourth factor is cohesion. So these are the four factors to measure the quality of the design. So if the quality is higher, then we can say the design is good. What is understandability? Understandability is something like the design should be simple, should be understandable when we read the description about the design, or when we look at the class diagram or something like activity diagram. They should be like in a way that anybody can understand the process or the structure easily. So for example, I can say like when we have a class diagram, the class names should be meaningful class names. Actually, like just by looking at that, we can I understand what are the real world entities we are considering. And also the function names, method names in the classes should be meaningful. So just by looking at the name of the method, we know that this method is responsible for this kind of process. So we can understand that. And also the variable names should be meaningful. And also the interactions should be simple and meaningful. Make the design simple in a way that just by looking at the description or the class diagram or activity diagram or whatever, somebody can easily understand that. So without understandability, it is very difficult to change the system or modify or whatever, like fixing bugs. Everything will be very complicated and difficult. And adaptability. Adaptability is another important factor of a good design. So if we have a good design, if we say the design is good, that should be easily adaptable. Like when we design a software and when we implement it, when the requirements are changing, when the technology is changing, or the like hardware configurations are changing, there should be a way to adapt our existing system in a way that it matches with the changing requirements. So sustainability of the system. So there is another way, like if we use some, let's say, uh, a programming language which is not supporting in future, no updates for future hardware system, something like that. So in that way, we can say our system is not adaptable. So we cannot use that programming language and extend our system further. at some point we have to stop uh, developing from using that programming language. We have to shift to another one. So our system is not adaptable. We may have to like re-implement everything. So this should be like kind of adaptable, and also that is like the implementation part, but also the when we use the class diagrams and everything should be adaptable to changing requirements. So adaptability is another important factor of measuring the quality of design. And these things, coupling and cohesion, we will discuss these things in very detail. For the time being, let's discuss a little bit more about the meaning of good design. So we know that software design is kind of a process of problem solving. So when we have some real world issue, real world problem, or something like to automate the real world process, we use software system. So in order to like, let's say like in a software design, it is a meaningful engineering representation of something to be built. So that is actually the design of the software. So that should be able to trace back uh, and find the customer requirements. And if something goes wrong, we should be able to trace back and say like, we try to implement the system addressing this kind of requirements likewise. So everything should have the origin. So to make the quality of this uh, building process, development process, software construction, like making a software is a kind of a development process. So it is ongoing. So to make this work very successful, we know that we have to like, we should be able to measure the quality of the design, and we should be practice in a way that we meet the high quality design, or the high quality like we are meeting a high quality design to construct the software. So we talked about first two things, understandability and adaptability. Now we are going to talk about cohesion. Cohesion is something like, okay. So cohesion is a measurement of the extent to which related aspects of a system are kept together in the same module and unrelated aspects are kept out. I think you can understand that idea. So it's like related components, related aspects, related functions, related classes, those kinds of things. The things which are related with each other should be kept together, and unrelated things should be kept aside. Even though we use them in the system, we make related things close, like keeping in the same package, something like that. For example, if we take a system for university, there are academic activities, students, exams, lecture scheduling, that sort of things. Maybe we can keep in one package all the classes related to that kind of process. But there are several other processes going on in the university, like payments and purchasing, likewise finance and research grants. So those things are not directly related to academic activities. So we can keep them in different packages, like package for accounting information, some package for like payment, some package for maintenance and payroll, purchasing. Likewise, we have to keep the closely related aspects, classes or things in different packages. So when we talk about this object-oriented concepts, object-oriented way of implementing or designing um, a class to be cohesive, the member function should be work together to achieve the common goal. So that means all the functions or all the methods we define in a class should be actually relate to that class. For example, if we have a function in the like system for a university, we have a class called student. There are all the functions we define in the student class that should be actually related to student, not for other purposes. So all the close like related things keep closer, and unrelated things they are kept apart. So that is the idea of cohesion. So I will type that thing. So cohesion is a measure of the extent to which the related aspects of a system are kept together in the same module and unrelated aspects are kept out. So when we talk about degree of cohesion, we can see like there are different types of cohesion, 5 types: coincidental, coincidental cohesion, logical cohesion, temporal cohesion, procedural cohesion, and the fifth one, informational cohesion. So these are different types of cohesion. So cohesion increases from this level to this level. Cohesion increases. So I'm not going to discuss about these different types in detail, but I will give you an assignment asking to discuss about these things. So you can refer internet and read about these things and write small description. So then it will be more effective that you can search it by yourself, and it will be more understandable for you rather than I'm explaining everything and giving the note. So these are the different types of cohesion, and we know that, like it is said, that cohesion is increasing when it coming from this first point to this point. So increasing the cohesion, or the higher cohesion, is expected for a good design. If to become a good design, cohesion should be higher. So that means informational cohesion is preferred. So that's about cohesion, and the other aspect is coupling. Coupling. So coupling is the degree to which components of a system depend on one another. So coupling is the degree to which components of a system depend on one another. Dependencies. Depending, if there are a lot of dependencies, we say there's a high coupling. And coupling increases when data exchange by the components become larger. So coupling increases when data exchange by components. One class sending a lot of messages, or a lot of uh, like sending parameters to other classes. That way coupling increases. So a lot of dependencies are there. So actually we know that it is not possible to avoid all the dependencies. There should be, there are some dependencies, because real world systems are like, real world scenarios are depending from one process to another process. But when we model that in software system, actual real world dependencies should be there, but we should not introduce more and more dependencies because of our implementation. So coupling should be like decreased as much as possible. So that is about idea, like having the dependencies. So coupling, if there is a lot of coupling, we say it is tight coupling. Otherwise, it is loose coupling. So loose coupling is preferred because there are no lot of dependencies. There are dependencies which are like kind of things like unavoidable because of the real world scenario, but we should not introduce more and more dependencies because of our implementation. So coupling should be loose. So the loose coupling is preferred in like good software engineering practice, but tight coupling may be necessary for maximum performances sometimes, uh, and sometimes it is unavoidable, but loose coupling is preferred. And types of coupling, like here we discuss about degree of cohesion, and here we have to discuss about degree of coupling. There are four types of coupling also: data coupling, stamp coupling, control coupling, common common coupling, and the fifth is content coupling. So you can discuss about, you can find out about these different types of coupling: data coupling, stamp, control, common coupling, and content coupling. Uh, so in a good design, we should have loose coupling rather than tight coupling. But perhaps tight coupling is necessary to get maximum performances, or uh, kind of efficiency kind of thing. So sometimes we cannot avoid uh, tight coupling, but still the loose coupling is preferred as a good software engineering practice. So let's briefly discuss about common design mistakes. So the first common design mistake is making concrete design. Making concrete design means we uh, do not keep a room for extensions. Make everything concrete from the beginning. So there are no interfaces, there are no kind of specialization, generalization concept like superclass, uh, subclasses concepts. We are not using that. Likewise, we use everything concrete from the beginning. But it is a design mistake. We cannot extend or we cannot reuse the same design there. So it is one of the major, like one of the common design mistakes. Producing concrete design, so kind of like giving too detailed components rather than abstract solutions. So when we are giving a design, we are like, it is better to have like abstract components, abstract classes, some kind of abstraction, deriving things from superclasses to subclasses. Likewise, that is preferred, but having everything too concrete is a design mistake. And another mistake is undocumented undocumented decisions. So every decision we take in the designing process or software engineering process, we have to kind of document them, keep track of the things. Then only we can understand what are the issues we met with and how we overcome from them, and why we use different design ways rather than using another way. Likewise, everything should be documented. And the other thing is open closed principle. So the design should be open for expansions or shrinking. We should not like uh, give a design or implement a system thinking that this is the final system. So our system should give some degree of freedom to expand it further or shrink it. Otherwise, giving a very rigid solid system is a kind of a mistaking software engineering process. So these are the three main design mistakes: making concrete design, undocumented decisions, and violating the open clause principle. And also, we are advised, as we discussed here, we are advised to like having high cohesion and loose coupling. High cohesion means all the related things should be kept closer, kept together. All the functions, all the methods in a class should actually relate to that class, and all the related classes and interfaces and super classes, those things should be uh, packaged uh, in the same package likewise, and all the unrelated things should be kept apart. And coupling means like the interaction between objects, so components should be less as much as possible. And these are the common design mistakes. So when we think about software design, software implementation, we have to consider these aspects as well. So the assignment I'm going to give you, I will upload deadline and document about that. Uh, that is about read and understand about these different types of cohesion and coupling, and describe them separately. Okay, so we will start discussion about design patterns. After this, I will come with that. Thank you.